So we made the case when we've been talking about groundwater flow that our interest is in maybe taking the most difficult case that we can to look at a non-aqueous phase liquid, which moves in the subsurface. Typically, it moves across the unsaturated zone, through the vadose zone, to compress the water table if it's an L-NAPL. And if it's a D-NAPL, can just keep on going through that and will be stopped by a capillary barrier. And that our interest in doing that is that we'd like to know what this architecture is of the in the subsurface as a prelude to maybe doing something about it, or maybe trying to understand exactly what the ramifications are for how quickly this stuff will go downstream or down gradient as being carried by advective flows. And so that's the premise that we've started with. We've always capped this instead of, or couched this in terms of the concept of multiphase flow. So flow of a wetting fluid and flow of a non-wetting fluid as two particular types. Usually for most of the stuff that we've done, we've dealt with water being the wetting fluid and the non-aqueous phase liquid being the non-wetting fluid, whether it's gasoline that floats on the water table or whether it's D-NAPL that goes through it. But because of that generic way of looking at things as multiphase flow, we can also use exactly the same concepts to deal with the vadose zone where the non-wetting fluid happens to be air. And so I thought we'd start off today by basically recapping what we've talked about in terms of that multiphase flow. And then what we'll end up doing is working on the concepts of unsaturated flow, where the second phase, instead of being a non-aqueous phase liquid, is actually a non-aqueous phase gas. It's air in our particular case. And our interest in doing that is, again, in just being able to demonstrate that the same relationships in terms of capillary pressure versus saturation and the relative permeability relationships also apply to those systems. And there are a number of empirical methods to be able to define those, one of which we've looked at already, which is Brooks-Corey, which you'll recognize when we go through it, and one which we haven't, which are these Van Genuchten relationships, which allow us to empirically define exactly what these components are, capillary pressure versus saturation and relative permeability relationships, so that you can apply them in your work should you so desire. So that's kind of where we're going with this today. So I thought we'd start out by kind of recapping exactly where we've come from. So let's do that. Just to make sure that these concepts are really cemented in your minds, because they're key. And so you remember that we've seen before this idea that if we start off with a water table, and that this is present below, say, a ground surface. That what we can do is, if we wanted to, we could define this relationship, well, that isn't the right place, where this is what we've called elevation. If we do it relative to the water table, then what we could do is we could define this as a magnitude of pressure. And if we do that, then we can look at the behavior of water in our system, both below the water table here and above it. And if we look at the distributions of pressure, they should look like this. If we have air in the system, then that would look something like this pressure versus depth relationship. And we know that this is the pressure changes as being equal to P is equal to elevation times the unit weight of air in this particular case. So this is the pressure distribution with depth for air. And I suppose if we have a DNAPL in the system, this is the most careful graph I think I've ever drawn my whole career. So this is water. And so we'll try and keep with these colors, and this is by definition DNAPL. And these all correspond to the same calculations, that this is going to be equal to the pressure being equal to elevation times the unit weight of whatever that fluid is. They're all fluids, right? Even air is a fluid. It's not a liquid, but it's a fluid. And so our reasons for doing that have been that if we look at, now if I try and draw a bit too far to one side, but let's do this anyway. If I draw a couple of graphs, and I'm just going to draw the capillary pressure versus saturation curves that we were looking at yesterday, Tuesday rather. And define exactly what those are. And so these are usually written in terms of capillary pressures, which are equal to the pressure of the non-wetting minus the pressure of the wetting fluid. This is plus VE, positive, and this is 0 here, and this is also positive here, increasing. So increasing from 0 in this direction, increasing in 0 in this direction also. Then we know that when we look at these relations, if I use kind of a generic color for these curves, then they look something like this, and they look something, the mirror image of that as we go down. It's not supposed to have this wiggle in here. And so the only relevant ones to look at above the water table, this would be the, by definition, this would be the vadose zone. Which we're talking about today. So in other words, fancy name for unsaturated. Of course, it's not unsaturated, it's actually partially saturated, so it's a misnomer, but nonetheless. And this is the groundwater zone. And we made the case before that when we look at these, this is very similar to, I mean, you'll realize, of course, that we're drawing this figure, I think it's, oh no, I think it's the second one down. So rather than just pointing at it here, we're kind of redrafting this figure, just to remind you of what we're doing. Then in each of these, what we are able to do is that because the unit weight of air is 1,000th of that of water, this is basically almost on this axis. And if we look at the capillary pressure magnitudes, then that capillary pressure magnitude is going to be this. Capillary pressure is equal to the pressure in the non-wetting minus the pressure in the wetting. The pressure in the wetting is in the water is going to be negative, right? It's in tension, because this is by definition the atmospheric pressure. By definition, the location of the water table is where atmospheric pressure is 0. If we go down, we know that pressure increases. If we go up, pressure decreases because we're kind of physically pulling it up. So the pressure of water is negative as we go up here, and we're subtracting from that the non-wetting fluid pressure, which is basically 0. So this is a negative value, so negative and negative value is a positive, so this really is a positive value. And so what this is physically allowing us to do is it's allowing us to be able to say that in this, the amount of water that we have would be the saturation. I didn't label this, of course. This is saturation of water, 0 and 1. And if we wanted to, this could be the saturation of the non-wetting, which would just be the inverse of that. And so this would be water. And if we use the same color scheme that I'm suggesting we use, this would be. So it immediately allows us to say something about the distribution of the saturations in them as we go up through here. If we can scale this vertical ordinate, not in terms of capillary pressure, but in terms of elevation, which we can, right, quite easily, I suppose it would be something like Z times unit weight is equal to pressure. And so if we just wanted to rearrange that, we could calculate, you could take pressure and you could divide it by unit weight. And that would give you elevation. So if you want to convert from pressure going upwards to elevation going upwards on this axis, so these are congruent with each other, then you just have to use this conversion here. Nothing more than that. And if you do that, then you have some a tension saturated zone that we talked about last time, which is this area here where it's below the bubbling pressure, PC0, which is the pressure at which this should be where it's right on this axis, before air can bubble into it. A bubble of air can get into it. It's in negative, it's in tension. The water's in slight tension. And above that, air can get into it in progressively larger and larger volumes as it saturates it. So it goes into the largest possible pore here first, and then it starts filling up the smaller and smaller pores that are connected in the system here. And that's exactly congruent with the behavior below the water table. And so this would be the capillary pressure. We draw it somewhere else. This would be the capillary pressure, which is equal to the pressure, again, in the non-wetting minus the wetting fluid. This is the pressure in the non-wetting. This is the pressure in the wetting. And by definition, since this is larger than this, it's going to be positive also. So in other words, the axis for this is positive, the axis for this is positive, and the capillary pressure versus saturation curve would look exactly the same. And so if we show exactly what we think that would look like, then I suppose if we take any particular, let me do it as a very fine line. If we go across here and I do this, then this is going to be saturation of water, and this is going to be the saturation of the non-wetting fluid. And so that's really the system that we have. It's no more involved in that. The other thing, so that's kind of the basic understanding. So these are the curves that represent the material. So you get a different curve for a different material. But if we put them in the right location, centered on the water table, both above it for the unsaturated zone and below it for the groundwater zone, then they both universally represent this multiphase flow behavior. One in which the non-wetting fluid is air, and one in which the non-wetting fluid, I guess, would be DNAPL in this case. So if you understand that, you understand almost all of the stuff that we've talked about in this class. So this is this is the way we usually look at these. This is it upside down, but that's the case that it is. And the only other thing that perhaps is worthwhile mentioning is that this defines exactly what the static condition looks like in terms of the equilibrium saturations versus either capillary pressures or depths, standard results. If we want to know the rates at which fluids flow in these systems, then we need something else, which is the relative permeability versus saturation curves. And those are just the ones that we've had before. Congruent, I guess, with this picture, it would look something like this. This again is the water saturation from 0 to 1, and it would be the non-wetting saturation from 0 to 1 in the opposite way. This would be relative permeability. We know that relative permeability scales is just a scaling value. And if we wanted to do it again for these conditions, then for water, I guess, well, what's the other thing that we don't necessarily have here? I'll use this color again. So this is, we refer to this as a drying curve, because water is getting pushed out. Perhaps more obvious here, water is getting pushed out by air, and in retreat it looks something like this. One would be the mirror image of the other. And the reason for putting that on is that now if we use this other ordinate here, then we know that the relative permeability curves, at least for water first, which is perhaps the easiest one to do, would look, let's do it, big honking, big thick thing, look like this, like this, would like this. So this is, whoops. This is a blunt instrument. This is the relative permeability of water, the wetting fluid. And I guess in either green or in red, we'd have to choose one of them. Let's choose red. Then the other curve would look like this, this, like this. And this, of course, would be the relative permeability of the non-wetting fluid. And this non-wetting fluid could be either a NAFL, D-NAFL in our particular case, or air. I guess air was... And so that, if you understand that, then you understand most of what we needed to know from the first three weeks of this class. We talked about calculating permeabilities. And when we talked about calculating permeabilities, or using permeabilities to calculate volumetric flow rates, then this is governed by this equation here. We know that if we're talking about flow, so just to back up, this is the behavior that we're talking about for the steady equilibrium behavior. It gets into this location, it's held by capillary forces, can't move, isn't going anywhere except by dissolution typically. If we want to be able to move it, then we need to use Darcy's law and relative permeability concept, and we can define that either as a volumetric flow rate being equal to a cross-sectional area of flow, a relative permeability which is a function of saturation of water, a permeability and a viscosity of the fluid that's moving. This is what we talked about last time. And if we're not completely rigorous, we can define behavior in terms of a pressure gradient. But we know that that doesn't always hold, because if we're looking at flow, we know that if we have in a swimming pool a pressure gradient that changes with depth, that's in a static fluid. So if this is finite and the flow rate is 0, this can't be quite right. And so what we can do is we could use this relationship here, very few relations that we use, to note that pressure is equal to elevation. So let's rewrite it as head multiplied by unit weight. We can think of an elevation change as being a head, a vertical elevation. And if we do that, then we end up with this perhaps easier to use, more universally useful relationship, which is the same as the one above it, relative permeability, which is a function of water saturation, intrinsic property of the material, which is permeability, intrinsic property of the fluid, which is viscosity, a change in head with elevation, which has no dimensions, and density and gravitational acceleration, which is just this term here. And so that's useful for us to be able to calculate flow rate. And so what we could also do is, since this is this universal term that we can use, which is much better than pressure, we used it last time when we went through the assignment, for example. So what does head look like if we go up and down in this system? And so if we choose another color, what color should we use? Something radical here. If I was to plot, for instance, the change in head, I'm only going to do it for part of this. So if this is head, and we know that we've defined head as equal to an elevation, a pressure, not a capillary pressure, divided by a unit weight of fluid. And just for completeness, to bring back your nightmares, Bernoulli term. And we're just going to say that the flow velocities in the system are very small. And all this term really represents is if you take a mass of fluid and you accelerate it at some velocity, that change in velocity has to act against inertia. And so this is only important when flows are high enough that the changes in velocities are large enough to have a significant part of inertia in the system. But if the absolute velocity is tiny, then by definition the change in velocity can only be tiny, and therefore we don't have to worry about this term. And so we're left only with these two remaining terms. And so what happens then if we go up within this fluid and look at how fluid pressures change? What's going to happen? If we look at this location here, and if we choose, as we have done, the fact that the datum is 0 here, then by definition the pressure here is 0, the elevation is 0, so if we plot head, the magnitude of head should also be 0. Okay? This is positive, and for Z this is negative. I guess I didn't say that before, but that's true for here as well, right? This is positive, and this is negative. Then, as we go down here, some amount, let's go in the water, the pressure at this point is going to be equal to positive pressure divided by unit weight. But the distance here is going to be equal to negative Z. And so when we add these two terms together, a positive value for this, a negative value for this, they're going to be exactly equal to each other, right? Because this is kind of the head. At this point is just in the swimming pool. So if you like, the pressure, the head at this point is going to be 0. They cancel out. By the same token, if you go up to somewhere here, and what we're doing, we're on this. If we go up to this point here, then this is also equal to Z. It's equal to a positive value, right? By definition, because we're going upwards. But we said that the magnitude of this pressure has to be equal to, pressure is equal to minus Z unit weight. I guess I did it slightly, yeah, this is fine. So this term now is a negative value. This is a positive value. And so the value of the head on this position is this. And so that's important. So it's exactly what you'd expect. If flow is being driven, I'll write Darcy's law up here. If flow is being driven by an area, a relative permeability, a permeability, and a change in head with elevation. So I'm just then if this term, the change in head with elevation, what's the gradient of head here with z? It's 0, right? It's the same here as it is here. It's aligned parallel to the z-axis. So this term, in this particular case, has to be 0. And so you'd expect the flow to be 0 as well. So it gives us exactly what we expect it to be. So if, for instance, the head was equal to something else, so if this was the magnitude of head, then which direction would flow be occurring? We can write that the velocity is equal to minus permeability over viscosity, rho g, change in head with elevation. In this particular place, this is head is increasing with negative z. So I guess if you draw a normal graph, then head increases as z decreases. So this is negative. This is always positive, and this is negative. And so in this particular case, the velocity would have to be positive. And so if the gradient looks like this, then flow has to be occurring in this direction. Because this is positive value of v. If you did the opposite, and you registered a gradient that was going in this direction, then this, by the same token, would mean that flow was occurring downwards. And so if you could measure in situ somehow the magnitude of how head varies with elevation, and you know what the unit weight of the fluid is, then you know by definition what the direction of flow would be, that it wouldn't be in equilibrium. And so it's important in our understanding of these. I guess it's a bit of a messy figure, isn't it, now I realize. Kind of artistically challenged, maybe. But it's important to be able to make the distinction between pressures and heads. So pressures vary linearly. They vary linearly if they're static, as controlled by the unit weights of the fluids, whether the fluids are very light or more dense or more dense. It's directly proportional to those. But the magnitude of this gradient of fluid pressure, if you convert the fluid pressures to a head, just using this simple expression that we have here, then that gives you some information exactly about where those out of balance fluids, what they would do in terms of driving flow. So if it's a static fluid, then the lines should look like this green, blue, and red in place. If that were the case, then the magnitudes of the head that you'd get for these fluids would all be right on this axis. It wouldn't vary from it. If you went into the subsurface and put a borehole in, and you measured the head locations or the head magnitudes and how they change with elevation, you can immediately say something about what is happening with regard to flow. And that would be that if it's oriented like this, it has to be flowing upwards. And if it's oriented like this so that it's increasing downwards, then it's flowing downwards. If it's increasing, if head is decreasing downwards, it's flowing downwards. If head is decreasing upwards, it's flowing upwards. And so you can always do that. So this, I think, is a useful figure to have. So that's why I wanted to spend some time on it. And it's a key issue from what we've dealt with so far in this class. Yes, Meng? This is, yeah, okay. So what is this? It's just the magnitude of the saturation that you find yourself at. So it's just saying that, it's just a way of saying that relative permeability is a function of saturation of water. And so for this, that would be this expression here. So it's saying that if the saturation is equal to 0.4, then the relative permeability is equal to 0.1. If the saturation is equal to 0.6, then the relative permeability is equal to 0.7. Function of. Function of, that's all. Yeah, so that's important. Just shorthand for writing function of. Okay, all right. So, that's a fantastic figure. So, I think. So anyway, so if you understand these curves on the right-hand side and what they physically mean, if you understand the meanings of capillary pressures and what they translate to in terms of saturation distributions in the static case, then that's important. If you understand, if we're looking at the motion of fluids, then we have to know something about relative permeabilities, which follow directly from saturations. And if we know that, we can use that directly in Darcy's law, and we can say something about rates at which fluid flow occurs, volumetric rates. And if we make this connection between pressures and heads in a very simple way, we can make a distinction by measuring heads as to whether flow in a gross sense is occurring upwards or downwards. And of course, you know, the reason for this is that this term here, flow, just like it would be if you have an upstream pressure, downstream pressure, and horizontal flow. It's exactly the same process which is driving the flow. Okay. All right. So, questions? Okay. All right. I'm going to go back to this, close this. So that's kind of the recap. So what we're going to look at now is this idea of matric potential. Actually, we don't really need to look at it because we can describe it in 2 seconds. We noted that the value of head is equal to elevation, fluid pressure divided by unit weight of the fluid, plus v squared over 2g. I guess we know that in a fluid, relative to some datum where z is equal to 0, then choose a point. And this is P over gamma. And this is Z. And that together, as far as we're concerned, these sum up to this most important part, and we throw away the other part. So when we talk about the term matric potential, it quite simply is just this term here. Bless you. So matric potential in the unsaturated literature. So we had a show of hands before. Are a bunch of you taking this soil physics class right now in ag? Yeah, don't need to show your hands this time. But if you've probably talked about that already in that class, I would guess, because it's a soil physics term. And it controls many of the things that we're dealing with. So we've talked about this. Sometimes it is given the term psi, I guess. This is exactly the same expression we've just talked about. And it's important because when we talk about these two fundamental relationships that we're interested in, capillary pressure versus saturation curve and relative permeability curves, that we can define those behaviors in terms of capillary pressures, the difference between the pressures in the two phases, air and water for unsaturated flow, or DNAPL or NAPL and water for saturated flow. And we can use certain relationships to define those behaviors. And we've broached one of them already, but let's spend a bit more time looking at it exactly. I think it's always behooves us to spend more time on it. And that is these Brooks-Corey relationships. So we'll talk about two different relationships. One is Brooks-Corey, which is this one here, which we've kind of introduced already. And it's useful because it basically allows us to be able to convert these curved figures for capillary pressure versus saturation into a straight line relationship. And it comes from noting that you can fit a curve to the relationship, which is defined not in terms of capillary pressures, but in terms of matrix potential. This is matrix potential. And the easiest way to maybe explore that is to explore it in a way that we've seen it before, which is as a curve that looks like capillary pressure, in this case divided by a constant, unit weight of fluid, that allows us to get a relationship that looks like this, that is defined in terms of saturation of water between 0 and 1. And you might remember that what we had done before was we took this cutoff here and labeled it as the irreducible saturation of water. By definition, this is the maximum amount of water we can get out of it. We're left with this saturation of water even after we've got up to a very high negative pressure, and define this particular value. And so what we could do is we could do two things. One is we could cut off this figure at this exact line here and define a new range of values, an effective saturation which is equal to 0, and an effective saturation which is equal to 1. So instead of taking it between these, we just move the 0 ordinate into this place. And then this length here becomes saturation. This just becomes 1 minus the irreducible saturation of water, bless you. And all this allows us to do is, instead of having this dead space on our graph, it means that we can plot this this effective saturation relative to capillary pressure, and it allows us to get a straight line relationship. The other thing that we could also do is we could define this not in terms of effective saturation, but of volumetric moisture content. So you remember that saturation is equal to the volume of water divided by the volume of the voids, whereas volumetric moisture content is equal to, again, the volume of water, but divided by the total volume of the solid. So which is the same as the volume of water divided by the volume of voids plus the volume of solid grains. So it's just a different way of calculating how much water is in the system. Instead of normalizing it to the void volume, so you fill the voids 100%, saturation's 1. You fill all the voids, so you fill the porosity, then this bounding value is just equal to porosity. So in other words, instead of scaling it with saturation, we can scale it with volumetric moisture content. We could also do that on this term here, and we could have an effective, whoops, not Q, an effective volumetric moisture content of 0 and an effective volumetric moisture content equal to 1, just by cutting off this part on the other side of the curve. And so if we do that, then we can use this relationship which defines the equation of that curved line. This is the volumetric moisture content we find ourselves at. This is the irreducible saturation of volumetric moisture content of water. So if we just draw a cameo to say what those components are. This is theta W0. This would be whatever the moisture content we find ourselves at is this. This is theta W0. And this would be theta saturated, which we've already said is equal to the porosity. So again, we're just defining the curve in the same way. Getting rid of this stuff on the right-hand side. And so if we know the volumetric moisture content we find ourselves at, this is a function of the porous medium as to what this would be. And this is always going to be equal to the porosity, as it turns out. And so what we could do is we could subtract this term here to this side here. And we could divide both sides by this term here. And if we do that, then we get something like theta minus theta W0 by take this term, dividing both sides by this. The saturated value minus the irreducible moisture content is equal to pressure we find ourselves at divided by the bubbling pressure raised to a power. So this is just the equation of this red line here. And so all we've done to it is define these behaviors. And I guess this term here would be PB, or bubbling pressure. Actually, we might do it as a matric potential, dividing by the unit weight of the fluid, of water in this particular case. If you divide one by the other, they just cancel out. And so this, you'll see, is exactly the same as this relationship here. So if you feel more comfortable with what saturations mean, then that's fine. This is exactly the same expression as this, but just written in terms of effective saturation. But all it really is, it means going across this magnitude from this particular end boundary here to see the relative location. So in other words, if this is drawn in terms of if this is effective moisture content, this would be 0 and this would be 1. If it was also equal to, I haven't left myself any space, the effective saturation, it would be exactly the same scaling. And so this is just a relative magnitude of the distance between the irreducible saturation of water to where it's 100% saturated. And so it's that component. And I guess we've talked about it before, but this clearly is the equation of, if you draw it in log-log space, this is just the equation of a straight line. So if you take logs of both sides, take log of saturation, you take the log of this side, then it's multiplier of this multiplied by the log of this ratio. And if you draw that as a straight line, it would look something, you could write it like this. Draw it like this. log of effective saturation, log of pressure divided by the bubbling pressure. So this is one term on the axis, this is the other term on the axis, and they're joined by this term here. So this is just the gradient. So in other words, it's the equation of a straight line. This is effective saturation, so this would be lambda, and this would be 1 decade, right? Not 1 unit, it's in log space, so this would be 1 decade in terms of this transit. So that's all it is. And this intercept here would have to be at logarithm of the effective saturation, is equal to 10 to the 0. In other words, 1. So in other words, the effective saturation is equal to 1. Right? In other words, 0 intercept. So the equation of a straight line, you could have an intercept in here, but you don't need it because actually on a log scale, 10 to the 0 means that, which is equal to a saturation of 1, gives you this straight line. So the reality is, or the implications are, that this black curve here transforms to being a curve that looks like this. And it's useful because it now has a very simple form, which is this. And we've talked about the ramifications of what that is in terms of exactly what that means. This is the bubbling pressure. So this intercept here is the bubbling pressure. And the gradient of this line, yeah, I've just flipped it on its side, right? This is kind of xy space. Y is equal to mx plus c. That's really what it is. And so this is over 1 decade in terms of pressures, which is this 1 decade here. And that's just the definition. We made these points before as to what the physical is. This a broadly graded pore space or a single graded pore space? No? Nothing? So here you invade in the biggest pore as you increase the pressure. Keep on increasing the pressure, you successively invade smaller and smaller pore space until you get to somewhere over here. Here you invade the biggest pore space, and immediately as you've invaded that big pore space, you invade all of them. So this would be very uniformly graded or uniform pore space. This would be a broadly graded pore space. If the intercept happened to be over here, you guys have answered these questions before, then this would be a broadly graded pore space where the biggest pore is smaller, right? You have to apply a larger pressure to push the bubble in, and therefore this is a smaller pore space that you have to gain entry. But once you get entry into it, then all the other ones are broadly graded and fill up slowly as you start filling it. Well, we've talked a little bit about that. So we'd like to be able to rationalize using this effective saturation, which is the length along this axis, to be able to define the change in saturation that just leaves out this portion for the irreducible saturation of water. So it's just changed the scaling slightly by using this particular term here. So we're using this term here to be able to represent an effective saturation. What we might like to do is be able to define these curves either looking like this or looking like this, just from knowing what our material is, not actually measuring it, because they're actually quite difficult things to measure. And so what we could do is we could attempt to empirically define exactly what these magnitudes are. And so the last thing that we'll talk about in this regard in terms of multi-phase flow are these other relationships, not Brooks-Corey anymore, but what are referred to as Van Genuchten relationships, which are indeed empirical. And they take basically the same form as what we've looked at now. Remember that in terms of the capillary pressure versus saturation curves, they look something like this. This is the one that we've used the most in terms of a saturation of water, 100% saturation. This is the bubbling pressure. As we increase the capillary pressure, we come up this curve. We asymptote to the irreducible saturation of water at very high capillary pressures. So this is the way that we've looked at it, defined in terms of water saturations. This is the actual saturation of water, not the effective saturation. If it was effective saturation, it would be this. And we can also define those curves in terms of water content between the residual irreducible water content or the residual moisture content and the saturated moisture content. They're exactly the same curves. They just have a different scaling in terms of saturation. And so all these relationships are that we can define the volumetric moisture content or the moisture content as a function of some parameters. And these parameters are determined in terms of the saturated moisture content, which has to be equal to the porosity, the residual moisture content, which we've also called volumetric content due to phi W0. And so if we know those magnitudes, then we can relate these curves merely by defining some parameters. And the parameters that control that are empirical parameters of n, m, and alpha. So the terms you see in here, we'd like to know how volumetric moisture content varies as a function of matric potential. So matric potential is the vertical axis, volumetric moisture content is the horizontal axis, and so we'd like to be able to define the terms that make this curve. And so this here is just the equation of this particular curve, where we'd like to know what this is as a function of the capillary pressure or matric potential that we define. And we can do that as a function of material properties, which are the saturated moisture content and the residual moisture content, which are these two values here. And by knowing what these material properties are that would be appropriate to the material. And so we'll come to this later, but basically, if you look at a variety of different soils, there are tabulated values of these individual residual moisture contents and the particular parameters that describe the behavior. That's kind of where we're going with this. And so what we can do is we can define a moisture content as a function of this relationship, if we know what these parameters are. Or we could define an effective moisture content, where this value here is equal to 0, and this value here is equal to porosity. So just using two different scaling values, nothing more than that. If we wanted to do it in saturation, we could do it the same way. And so they're just between these limits of the irreducible saturation of water and where it's fully saturated with water. Again, with these individual terms of n, m, and alpha, which describe behavior. So these are material properties. And they would be different for a sand or a silt or a clay. They'd have different magnitudes. But if we know what they are, then we can define exactly these curves. So I'm never quite sure how useful it is to go through these relationships, but you can use, we can define these terms, and they're linked together in some particular way. And the value of this n term is a function of m, and a value of the alpha, remember we said there are terms n, m, and alpha. They don't necessarily mean anything. Actually, this means something. this is proportional to 1 over the bubbling head, what we've called HC0. We'll talk about that in a moment. But if we know what the value of M for a particular material is, we can calculate N. If we know what M is and the bubbling pressure, we can calculate the value of alpha. And so we can use these terms to be able to reconstruct, if you like, these capillary pressure versus saturation curves. And Fetter goes through this and defines these the method of doing it. It's really just a recipe. It might be worthwhile just going quickly through it. I don't think we'll ask you to do it in this class, but it's something that is just a recipe. So if you want to be able to determine what the values of N, M, and alpha are, and you had a curve that describes the capillary pressure versus saturation curve. This curve looks something like this. This could be a real curve. We can define some particular ordinates on this. The one ordinate is the maximum amount of water we can get out of it, and that is that the irreducible saturation of water, or in this case its moisture content, is equal to 0.1, right? This term here. When it's fully saturated with water, this is equal to 0.5. All the pore space is filled with water. And so those, if you like, represent the endpoints of this curve. Then the recipe is to do this. We define this point here and this point here. And we look for the point that's intermediate between them. So the average between these two is the point that is halfway between these. And so in this case, this length and this length are equivalent to each other, and that defines this point here, which we're going to call theta p. So in other words, take the average of these. In this particular case, this is 0.1, this is 0.5. By definition, this is halfway between. We have this point. We need to know as a characteristic, kind of harking back to this idea here, we saw that for Brooks-Corey, we could take a graph that looked like this, which has a curve in it, and we could make it a log linear curve. And so this is the same case here, is that we'd like to be able to figure out exactly what the slope of this curve is. And you'll see that on this curve, this is a log scale on the vertical side. It looks like it's a linear scale, but it's actually a log scale. And what we're going to do is we're going to draw this curve that is a tangent to this point at P, which is this. Goes through this point. It's tangent to this curve. And we want to know what this curve looks like over one log cycle. So one log cycle is here, and one log cycle is here. This is 10 to the 4, this is 10 to the 2, this is 10 minus 10 to the 3. And so this here is one log cycle. And so if we measure the slope of this curve, this blue curve here, between this point here and this point here, this is one cycle. This is the magnitude across one log cycle. And so this is this magnitude. So if you take it off here, this goes between something like 0.15, and this point here is 0.5. And so this length is, well, it might be, make this 0.16, I guess, right, to make that right, in terms of this. So that's the slope in terms of one cycle at this particular point. We non-dimensionalize the slope between the lengths of these two saturations, which is this term here, and we get a value of this non-dimensional slope, which is 0.85. And then we have two choices. If the magnitude of this non-dimensional slope is between 0 and 1, then we use this particular expression. And if the magnitude of this slope is greater than 1, then we use a slightly different expression. And so we know what this is in either case. It's just a curve fitting procedure. And so we get a value of m out of this. So that's our first material property. If we know what the value of m is, then we can also get the value of n, which is our second material property. And if we know the value of m, and we also know this, I'm just going back up here, the value of the bubbling pressure, so I'll make it smaller so you can see. So if we know what the value of the bubbling pressure is, this is where this deviates from the vertical, right? This is the first bubble of air that goes into the system in this matric potential. And this is actually just divided by unit weight. This is actually a pressure head in this case, right? This is actually this curve is actually matric potential, right? Which is just pressure divided by unit weight, units of length. And so if we use that magnitude in this, we have everything we need, and we have a value of our third parameter, which is alpha. So it may seem kind of circular to do that, because we said we wanted to be able to use this to not calculate, to measure these curves. And what we've done is we've taken a curve and we've calculated the parameters for it. But of course, if this curve is for a silt, and we think that all the capillary pressure versus saturation curves are going to be the same for all silts, then all of a sudden we now have material properties which absolutely describe the behavior, the shape of that curve for that particular material. Yeah, go ahead.
Why is alpha said to be approximated to be 1 over the pressure over the specific?
Because it turns out that the only of these three properties that has a physical meaning is that basically the value of this term here is equal to 1 over alpha. Oh, not that one, sorry. So this particular height here, which we've called HC0 before in some cases, is approximately equal to, not exactly, approximately equal to 1 over the value of alpha. And so if you look at the units of this, you can't tell that from here. So as in many things, we can't necessarily define that. It's just a relationship which falls out of it. But you can check the units. The units of matric potential are pressure divided by unit weight. They're units of length. And so this term here is equal to 1 over length. And so this also has to be terms of 1 over length, which is exactly what this is here. And so if you know the value of alpha, usefully, you immediately know the value of the bubbling pressure. So it turns out. So kind of a long and involved recipe, if you like, but but really all it's doing is it's allowing us to be able to get these material properties, numbers for these material properties, which represent the behavior of different types of materials, from which you could construct, if you wanted, these relative pressure versus saturation curves. So that's the first useful thing to come out of it. You might not think very useful, but it is. The other useful thing is that we've always made the point that when we've talked about these behaviors, that there are two properties that we like to be able to determine. We like to say something about what this capillary pressure versus saturation curve looks like. This is probably the best one for us to use, right? Because this is the right way up. And so what we've been able to do is define that directly from these curves. And this curve here, and importantly, I suppose, we should make the point that really we're only talking about one of these curves. And that is that the one curve that we have is just going to be the drying curve. Doesn't want to draw. And so when we look at Van Genuchten's curves, it doesn't like that for some reason. This is the curve we've talked about. We've only talked about the drying curve. It doesn't exist for the wetting curve, so we've only done it for one of them. The other useful thing that we'd like to get out of this is maybe to know what the capillary pressure, the relative permeability curves would be. And so in our particular case, the relative permeability curve that we'd like to be able to get some idea of would be this curve here for water. And so in the same way that we talked before about relating capillary pressure versus saturation curves and relative permeability curves to each other, we can do that using these relationships for Van Genuchten by using, again, this same kind of excruciating description of coefficients, but it allows us to be able to determine the magnitude of this term here, and that is this relative pressure, this relative permeability term. And so what we can do is we can define, if we wanted to define this value here, which is non-dimensional, we could calculate it as a function of this. This term here is what we've called relative permeability and relative permeability of the water. We can define it in terms of effective saturations, or we could define it in terms of heads. This is probably the most obvious one for us, right? Because we've talked about these curves as looking something like effective saturation between 0 and 1, a relative permeability that looks something like this in a very simple way. But in reality, I guess we've also made the point that it actually doesn't quite look like that. Right? It actually looks more like this. So this relative permeability versus saturation curve is defined again as a function of these coefficients. The value of m, which is here, and that's it. Only the function of the value of m in this particular case. So what it means is that in addition to being able to define the capillary pressure versus saturation curves for the wetting fluid, this is capillary pressure, then we've defined both of these terms. The drying curve on the previous discussion we had, and now the relative permeability term, which we can also now define. And so we don't have to guess them and don't have to substitute these simple x curves that we've used in the past, but we can actually construct them should we want to. The reality is that in models that are numerical models, we'd like to use these kinds of very accurate curves there. But for many intents and purposes, for the things that we'll do in this class, these kind of back-of-the-envelope calculations, then we can probably get away with somewhat slightly simpler relationships. And so the final slide, I think, well, not I think, I'm pretty sure it is the utility of this is that we can define these two things. So they're summarized, if you like, in this little slide. And that is that the relative permeability versus effective moisture content is given by this equation. So this is our Kr versus phi effective term, and the other relationship which links effective moisture contents with capillary pressure distributions are given by these. So that's the end result. And the utility is that these individual terms, which we've now switched to being beta and gamma in this particular expression, we've just switched symbols, that's all. What we called m before is now gamma, and what we called n before is now beta. If we know what the values of these physical parameters are, together with our value of alpha, then we can define these curves absolutely. And that's really our goal. And this table on the bottom right-hand side is a table that basically exactly does that. It defines a value of n, which is also called beta here. It defines a value of alpha, which we just discussed is equal to 1 over the HC0, the bubbling head, and the magnitudes of the bounding values of moisture contents for these things. So from this information, for any particular material, for a clay, for a silt, for a sand, you have enough information to be able to construct both of these relationships, should you want to. You can make this, or you can make this. And so, to reiterate, those are the magnitudes that we need to be able to say something about what the equilibrium saturation is with depth in the subsurface, and how quickly we can remove it. And this is what fits into this kind of formalism that we've talked and we spent some time talking about today, is that what exactly these curves look like in terms of above the water table and below the water table. Defining exactly what the saturations are, and also defining how quickly we can remove material from it. Okay.